Hello, this is Dr. Hassan Abdullah with the course Introduction to Natural Language Processing. And the topic in this video lecture is part of speech tagging. And the subtopic is Markov model. And of course, we'll also touch upon the Viterbi algorithm also. Both are crucial for part of speech tagging. And the supplemental website for this course is ezmcq.com/goget. So this basically ezmcq.com/goget is a learning management system which has very useful features. You can personalize your learning by setting the interface, by setting the type of questions you would like to see, and track your progress and track your learning also by doing the MCQs and also perform a search and so on. So all those details are given in these videos, which I would suggest you to watch to get the maximum benefit from this course. And these are the topics which are covered in this course. And you can see that we are at topic number 5, which is part of speech tagging. And now we move on to the learning management system. You can see that we have core computer science courses here, along with cutting edge courses like natural language processing, artificial intelligence, machine learning, and so on. So let's move to the course of our interest, which is natural language processing. And then we move to the topic of our interest, which is part of speech tagging. And part of speech tagging, these the first 5 set of Q&As we have already covered. And we have also covered the next set of Q&As, questions and answers, and the one after that also. So where here we are, and basically we have covered, so inclusive of this set of Q&As, that will be 91, about 91% coverage. So let's go to the topic and the Q&A. Briefly describe the main part of speech tagging techniques, what those techniques are, because we'll be using and discussing the Markov model and the Viterbi, which are PoS techniques. So there are the rule-based tagging. So rules are made that if this is the word and this is going to be a noun, this is going to be followed by this, so and so on. So these are the rule-based tagging techniques. Then there are stochastic and statistical tagging techniques, which look at the numbers and their probabilities and their occurrences of the frequency of the words. And based upon those frequencies, it is determined that what should be the tag of this word. Then there are transformation-based tagging, machine learning. So based train the model showing different training data, and deep learning based tagging where those parameters are set by the machine itself, and the hybrid systems. So let's go over them very briefly. So the rule based is, for example, provide possible tags. A set of rules is applied, and they are handcrafted rules. So let me open this for you. So these are handcrafted rules, right? So humans create those rules based upon the surrounding words, the context, and the syntax, right? So, for example, the cat runs. The word cat will likely be tagged as a noun, and it is followed by a determiner. Okay, the cat runs. So this is how these rules work. And of course, they are labor intensive, and therefore they lack the scalability and the volume of the work. All right. So let's move on to stochastic, which is hidden Markov models. So the hidden part is that the words are there, but the tags are kind of hidden, so to say. Okay. So, and of course, we use the transition probabilities from one state to another state. So basically, we are seeing the effect of the tags. The effect. So the tags are hidden. I'll go into more detail. So let me mark this for you here. Based upon the using transition probabilities, the probability of transitioning from one tag to another or one state to another. So the uses the probability of a word appearing given its preceding words, right? I eat an apple. So eat would be tagged as a verb and apple as a noun. So I eat an apple. So of course the apple is also with lowercase a. And the disadvantage, it requires a large corpus of annotated training data. Of course, with that takes time and effort. Then let's move on. Transformation based tagging. Let me mark this for you. Okay. Based upon statistical methods. Okay, combines the rule and the statistical methods, simple rule based methods, then a sequence of transformation rules to correct the misclassification. Right. So this is a kind of a best of both worlds, and combine the simplicity of rule based with the flexibility of the statistical learning. So this is going to be performing better. And machine learning support vector machines, decision trees, which are covered in the course on machine learning. Or if you want to know about them, you go to the main page of this learning management system. And in the yellow box, you can type decision trees within square bracket, or you can type SVMs, and then you will get all the useful question and answers and the explanations and everything. So, for example, if you look at here, so we have he runs quickly. The word runs would likely be tagged as a verb, quickly as an adverb. based upon these machine learning techniques. And then we have the deep learning part of speech tagging techniques. Okay, we have the different models, and which the deep learning is a complete course also, which I also teach. And you can know about deep learning by going to the main page and typing deep learning in the yellow box. So basically, this helps with lot of non-linearity and the sentence structure and long range dependencies. And a hybrid is basically is the rule based combination, machine learning and deep learning and so on. So trying to get the best of all the worlds. So the issue with the simplest stochastic probabilistic tagger for this particular statement. What we are going to do? We need to identify which is a noun, which is a verb, which is an adverb, which is a pronoun, and so on. So that's what we need to identify. Now this statement is very tricky because why it's tricky? Because there's ambiguity of time. Okay, time as in clock or time as in uh, kind of a historical event. Ambiguity of fly as an insect or flies as something flying, and ambiguity of like. So I'll show you why these ambiguities are there and how to handle them. Because of these ambiguities, there can be different taggings, and those taggings may or may not be correct, all of them. So ambiguity of time is money. So over here, time is a noun, and the verb I will time the race. So it is a verb. Time flies like an arrow. So for the simplest tagger, there would be kind of difficult. Okay, then the ambiguity of flies, the bird flies is a verb, and the flies can are buzzing. The flies are like an insect. And ambiguity of like verb, I like this. Okay, he runs like a cheetah. Time flies like an arrow. So there's ambiguity here. Is like, what is meant by like as in liking, or like as in association. So lack of contextual understanding. So when the context is not there, so there can be multiple part of speech taggings. Okay, because of the ambiguity in the wording itself. So over reliance on word frequency is going to create problems if we just rely on the frequency of the words. So if this is one possible tagging, this is another possible tagging, and this is another possible tagging. As you can see that the statement is the same, but the tagging is different over here. So in this example, time is a noun. In this example, time is also a noun, and over here, time is a verb. It's very different here. And if you're interested to know more about it, there are the references. So what are the Markov models? So the Markov models basically they define states and the transitions between the states, and the states don't have a history. Whatever happens is based upon the current state. That is the Markov property, and there are different types of Markov models, and one of those types is hidden Markov models. So these are statistical models, okay, and they describe as the system undergoes transitions from one state to another, and the future of the system depends upon the current state, not on the sequence of events. So so that's the Markov property. And one of a and from when the system moves from one state, it moves to one of the finite number of states with certain probabilities. Okay, those are called as the transition probabilities, and there's a transition matrix also. I'll show you all of this. And the Markov property, the probability of transitioning to the next state depends solely on the current state. It doesn't depend upon the prior states, and it also does not depends upon the sequence of the prior states. The sequence of the prior states is covered by another model. So types of Markov models are transition occurs at discrete time. So there are discrete Markov model as opposed to discrete. There is a continuous Markov model, and there is a hidden Markov model. The system state is not directly observable. Okay, so and only the outputs are observable. For example, if I could give you an analogy, so if we see if the ground is damp or it's wet or it's dry, so maybe it is because of rain, or maybe it is because of rain and a thunderstorm, or a combination of something else with certain probabilities. So let's look at example of Markov chain, visible Markov chain, not the hidden one, visible one. So we have these three states: sunny and cloudy and rainy, and then we look at the example itself. Okay, so we look at this example. So this we have already discussed that what is Markov chain, right? And discrete time events we are looking at. So let's imagine a simple system with three states, and they are before you, and there are the transition probabilities. So 70% chance that tomorrow will be sunny. So from moving from sunny to sunny, and 20% chance that tomorrow will be cloudy. So moving from sunny to cloudy, and of course there are all these nine probabilities. Okay, and we have a transition matrix also corresponding to these probabilities. I will show you right now. So now let's consider the scenario. Day one, the weather is sunny. Day two, the weather will be sunny 70% of the time as per the transition matrix, as you can see. And day three, if it's cloudy, and so on. So this process repeats the system, and the system evolves over time. Okay, and it is a probabilistic model. So if I zoom it here, you can see that from sunny to sunny is 70% probability, and from cloudy to sunny is 30%, and so on. So this is the basically the Markov model which we have created, and you see that it is not based upon what had happened earlier. Okay, so basically how it is applied, it is applied that if this is the tag of a word, then based upon the Markov model, what would be the tag of the next word? This is how it's going to be used, and it has been around for about like more than 100 years, 125 years, something like this. So what is the hidden Markov model? So that this is the visible Markov model. Then we look at the hidden Markov model. So in the hidden Markov model, so there is the definition of the something which is hidden, and there are the hidden states and the observations. And let's look at the details. So the system transitions between hidden states over time. The system moves between the hidden states, and the observations corresponding to those states are generated, which are probabilistically related to those hidden states. So we don't see the hidden states, we see the effect of the hidden states. Okay, so hidden states are unobservable states of the system. We cannot observe them. We can observe the outcome of those states. Okay, for example, speech recognition, there are the phonemes and then audio features, right? And we observe the audio features. Okay, so Markov assumption is that future state depends only on the current state and not on the sequence of previous states. Okay, and that sequence of previous states is covered by the Viterbi algorithm. So we have this state set of hidden states, and we have the transition probabilities moving from one hidden state to another state, and then we have emission probabilities which relate to the hidden states and what we observe because of the transition of the hidden state. Okay, and then we have the initial state distribution and so on. So this is one example. I'll show you the working of the hidden Markov model also. So these are the observable states. We have the land is dry or damp or soggy, and we have the hidden states. So it could be due to sunshine or a combination of sunshine and rainfall. So these events have their own probabilities, right? And so based upon these hidden states, we don't see those hidden states, cannot observe them. We can observe these states. So these are basically the words, and these are the tags. Okay. So we see the effect of tags, and based upon the effect, we assign the tags. Okay, so let's look at the simple example of hidden Markov model. Okay, so let me go into details. So we have the statement is the time flies. Time flies. So we have the noun, the verb, and the article or determiner. Okay, the time flies. You can say that the is the determiner or it is the article. And let's look at. So we have to define the transition probabilities. The probability of a noun being followed by a verb. So this is based upon the training data. Okay, this is based upon the training data. So a lot of data was there based upon which the system was trained, and this is the probability of a noun and then a verb, and a verb then an article. All right, and let me clean this, and of course define the emission probabilities. Likelihood of observing a word given a particular point part of speech tag. Okay, so what is the probability of time conditioned upon a noun? Probability of flies conditioned upon a verb, because remember that that flies can also be a noun as an insect. So depending upon what the system was trained, so it is going to respond accordingly, right? Okay, well then we apply the Viterbi algorithm. Dr. Viterbi is at the University of Southern California. I also did my two masters from the University of Southern California. So basically based upon this, the sequence is established, and we have the final part of speech tagging. So time flies like an arrow. So noun, verb, preposition, and article. So this sequence was established by the Viterbi algorithm. And this is a diagram which shows all of this. I hope you understand this. So then, of course, if you are more interested, you can do a part of speech tagging over the net. Also, there are many tools actually, online tools. There's 7 or 8 tools very popular. I've just listed some 3 of them. So the Spacey tool, which is based upon the pre-trained models, and it is written in Python. Python is a very powerful and very effective language, and I'd use Python in certain courses. As a matter of fact, in this course, the projects is NLTK, which is the Python library for natural language processing. And of course, this is powerful and works in real time also. Then we have the Stanford part of speech tagger probabilistic, which is based upon context-free grammar, which is covered in parsing, and of course based upon hidden Markov models. And then we have the NLTK part of speech tagger Python, which I mentioned here, and which is based upon pre-trained models. So a lot of work is going on, a lot of tools are here, and a lot of prospects in this area. So thank you for your time. So we finish this topic and subtopic.